So yeah, some words to myself. I'm now working since 12 years almost with biochar and water and wastewater treatment. And yeah, so since 6 years, I moved on to the production of biogenic activated carbon to replace, yeah, fossil activated carbon. I just on the laser pointer. And that's what I would like to present here as some of our results together with my colleagues, which are mentioned on this slide, all from the university. But yeah, first, why activated carbon from biomass? In Europe, environmental protection is gaining much more of interest, in particular organic micropollutants or trace elements, and wastewater treatment plants are the point source for the discharge of these OMPs. And they are only partly degraded in the normal biological wastewater treatment plants. Of course, they have potential negative effects on humans and environment if they enter the aquatic system. And to overcome this problem, a fourth treatment step is required. And one solution is to add activated carbon in a fourth treatment step, which will be mandatory in the European Union by 2045. So typically the normal wastewater treatment plants ends here, and this is a schematic drawing of an absorption stage with powdered activated carbon. So it works quite well and is established also in Germany. The main problem is that the production of activated carbon is associated with up to 18 tons of CO2 emissions per ton of activated carbon produced. And so our aim was to replace hard coal-based activated carbon by biogenic ones. So we were looking what kind of biomass are suitable for a thermochemical conversion, which are available and have a low competition of use, a high carbon content and a low ash content on the other side. And unfortunately, wood, there are some ecological restrictions. So on this flowchart, on the Sankey diagram, you see the potential of woody biomass of residual wood in Germany. And unfortunately, all available residual wood is almost used. So it's not really a sustainable solution to produce activated carbon. So then we were looking into residual grassland, which has the advantage that it's available in whole Europe. Also, grasslands provides a quite impressive contribution to ecosystem services. The problem is it has a very heterogeneous composition with a high ash content and a low high mineral content as well. So it's not suitable for direct utilization. And this requires a kind of a pre-treatment, and we were using the so-called integrated generation of solid fuel and biogas from biomass concept, short IFBB concept, for treating such grassland biomass. It's a hydrothermal treatment where the biomass, enzyme biomass, is hydrothermal treated with water at 40 degrees roundabout, and then mechanically dewatered, generating energy-rich press juice, which contains a lot of the minerals and ash. So this press juice is used in a biogas plant to produce biomethane and of course fertilizer. And the solid phase, which contains a large share of the carbon and fibers and is mineral reduced, is then dried, compacted. So we are using a pellet press to compact it, and is suitable to be used either as solid fuel or, in our case, as a feedstock for biochar or activated carbon production. So in this study I would like to present, we used some small lab scale auger reactor, which you can see here on the right side. And as feedstock for the process, we used orchard meadow and wet meadow, two different landscape conservation materials from South Germany. The process temperature was 900 degrees and the residence time of these pellets in the reactor approximately 25 minutes. And we applied also steam as an activation gas to the reactor, so it was more a steam gasification. And the steam was applied in different ratios. So we calculated the molar or the moles of carbon which we fed into the reactor, and then we applied 0% for high temperature biochar, let's say this way, 50% and 100% of oxygen by steam to oxidize 50 or 100% of the carbon, which is simplified in the reaction here. The generated activated carbon was then grounded to powder activated carbon, and we conducted some adsorption trials and batch adsorption trials using municipal wastewater from a wastewater treatment plant, and we applied different dosage of activated carbon, 0 milligram for the reference, 5, 10, 20, and 40 milligram per liter. So since the OMP concentration was a little bit low, we spiked it so that we had a concentration between 1 and 4 microgram per liter, investigating 15 different OMPs in this study. Since we are talking about biochar or activated carbon, also some characterization parameters. What you see on this slide are first the characterization of the biomass. So in brackets in the raw silage and before the values for the generated press cake. And as you can see, we are reducing the ash content by roughly 50%. So from 20% in the orchard meadow, which was quite old, to 10%, and from 5.5% to roughly 3%. Also, and this is mainly also important for thermochemical conversion, the sulfur and chlorine content was drastically reduced, which increased also the in total higher heating values. So, but this was only some of the results to not overwhelm you with all the other minerals we analyzed. And for the activated carbon, you see this here now for the orchard meadow and for the wet meadow at different oxidation potentials. So by adding different steam quantities to the process. Overall, the ash content increased with increasing oxidation, which is typically. So we had a high ash content in the orchard meadow, which results also in a high ash content in the activated carbon. The wet meadow with a lower ash content had a significantly lower ash content, but this was also higher than the two commercial activated carbon we used. So yeah, this is what you see here. We also did some further analysis in terms of the physical properties. First of all, I would like to mention the conversion rate, so from the dried biomass to the final activated carbon. What we see also is a decrease in the conversion rate with increasing oxidation from more than 20% to less than 17% for the orchard meadow, and from 17 to 12% for the wet meadow. Unfortunately, we do not have data for the commercial activated carbon. For this presentation, I only would like to highlight something in terms of the specific surface area, which was measured as BET, where we had more than 1,000 square meter for the commercial activated carbon, less than half for the wet meadow, and even less for the orchard meadow. The same for the total pore volume. Roughly half of the total pore volume for the wet meadow, and even lower, less for the orchard meadow. But I would also like to mention that most of the surface area from the commercial activated carbon are caused by the micropores, so which means less than 2 micrometer with 700 square meter. which is not really accessible in the wastewater treatment, but I will come to this later. And if we focus only on the mesoporic volume, we see that, yeah, also there we had a lower mesoporic volume for the wet meadow with 23 cubic centimeter per gram compared to 0.35 cubic centimeter. And also there, the orchard meadow was quite lower. So that's enough for the characterization for our study. So what we did, I mentioned this, we investigated 15 OMPs. To not bother you with 15 plots, we combined these OMPs into 3 groups. The first group, which contains benzotriazole, carbamazepine, diclofenac, and so on, is defined by the competent Center for Micropollutants in the state of Baden-Württemberg. And these OMPs are regular monitored and should be removed by 80% over the year in the wastewater treatment plants. In the second group, we included the remaining pharmaceuticals from this COMS B list. And in the third group, we included also the X-ray contrast agents. And what you see here is the OMP reduction at different dosage levels in gray and black for the commercial ones. The brown ones are the orchard meadow, and the blue ones are the wet meadow. And what I would like to highlight is that first of all, there is a difference in the commercial activated carbons. So the WP235 performed really well. For the biogenic ones, we see that the wet meadow was almost reaching the same reduction than the commercial ones. And we see a clear increase also in the adsorption or in the removal by increasing the oxidation potential or with increasing steam application. So which you can see from the dark blue to the light blue. And the orchard meadow was, performed not so well. The other one I would like to mention is that with increasing numbers of OMPs we considered in these groups, the removal rate decreased. You can see this from the left, group 1 to group 2 and group 3. So nevertheless, our aim was to compare the overall performance and also to calculate how much AC we need to achieve a certain reduction. So that's what we did, and what you see here on this figure. So we calculated how much AC we have to apply to achieve 50% reduction. In comparison to the NORAD SAE Super, which is the gray one and the figures above. So the red line is simply an illustration for the reference of the NORAD SAE Super. The black one is the second commercial activated carbon where we needed less, so roughly we had to apply only 60% of the dosage. And what you see is that the difference in orchard meadow and wet meadow is quite significant. We see a clear reduction by increasing the steam we applied. And if we focus only on the total COMS B list with the wet meadow, we almost reached the same dosage as the NORAD SAE Super. So we met the same reduction at the same dosage level. And we identified that the main influencing factors are the applied oxidation or the applied steam. So if you apply more steam, the required quantity was reduced. But also if we have a high ash content in the biomass, we need more activated carbon, and a higher mesoporic volume results also in a reduced activated carbon, which has to be implemented. Also, we measured the UV absorbance, which is a quite good indicator to estimate or to predict the reduction of dissolved organic compounds for all the investigated activated carbons and for the OMPs. And here on the lower figure, you see the correlation between the OMP reduction and the UV 245 nanometer reduction. And we have really a good correlation in the OMP and UVA reduction. And the UVA reduction is a commonly used tool to monitor the performance of activated carbon and wastewater. And there we see also with increasing numbers of OMPs considered, we need more. We need a higher reduction of the UV adsorbance. So for group 1, only 6% corresponds to 50% reduction. For group 2, 11% reduction in the UV absorbance is required. And for the group 3, we need roughly 15%. This is slightly important for some kind of an outlook, to keep this in mind, that we have a good correlation and the UV absorbance is good in the prediction. We use these data also to calculate an LCA. So there I must mention that the experimental boundaries and the greenhouse gas boundaries differ slightly. While we considered the landscape, or let's say the landscape conservation biomass in the experimental setup, we haven't considered the harvesting, so mowing and transportation in the greenhouse gas balance. So we applied a gate to grave approach, including the biomass processing, the pre-processing, the pyrolysis and activation, the application and the wastewater treatment, and finally an incineration of the spent activated carbon with the excess sludge from the wastewater treatment plant. And we used the quantity to remove 50% of the organic micropollutants. And here I would like to focus only on the total COMS-B list, also because we are running out of time a little bit. So keep in mind, behind these values for the LCA, it considers different required quantities to remove really 50% of the OMPs. On the left side, we see the savings due to biogas yield, reuse of excess heat from the pyrolysis, and on the right side, the emissions by heat, electricity, material handling, and so on. And the white bars represents the net balance. And I was quite surprised that even we need a higher quantity in terms in comparison to the really outstanding performing commercial activated carbon. For the wet, or for the AC from the wet meadow, the greenhouse gas emissions was only 1/10 or 10 times lower than for the commercial ones, and even much lower than for the second commercial activated carbon. And even the really not good performing orchard meadow had a 3 times lower greenhouse gas emission by achieving the same OMP reduction than the outstanding commercial activated carbon. So this was really a quite interesting results for us. Nevertheless, our aim was to further improve the whole process. So we moved on to urban waste. So we selected hedge trimming from landscape conservation and kitchen waste as some other waste materials. I don't want to dive into all these figures. I guess it will not be sufficient or suitable for this. I would like to highlight two things. So we applied the raw kitchen waste as a subfraction of bio-waste and an IFBB processed kitchen waste. So we measured also the surface area and the pore volume. And also for another second commercial activated carbon. I would only like to highlight two things: that with these edge trimming, which is not a really high value wood biomass, we achieved almost the same surface area as the conventional activated carbon, also the same pore volume, but a higher mesoporic volume. The kitchen waste, yeah, I must admit, half of it, half of the surface area, and even less in terms of specific surface area. So we were a little bit surprised to see the outcome there. And we see really no significant difference between the IFBB treatment or not. So we analyzed also the UV absorbance and the organic micropollutants. Here you see the relative demand, which is required to remove the same quantity, also 50% OMP reduction, in comparison to the NORAD, the reference AC, which is illustrated by the blue line. The circles represents the UV absorbance reduction, and values above the blue line means we need more, we need a higher quantity. Values below the blue lines means we need less than the conventional activated carbon. And simply to summarize, and the circles are the calculated demand based on the UV absorbance. And you see a quite heterogeneous pattern here. I would simply summarize that the conclusions: activated carbon produced by the hedges are performing better or equal than the conventional activated carbon. We see also here we compared different residence time, 20 minutes and 30 minutes. So in general, with longer residence time, the required quantity is reduced from the activated carbon. Effect of the IFBB treatment on kitchen waste is unclear also. In general, we need up to 2.5 times the amount of activated carbon if we are using kitchen waste for instead of instead of fossil-based activated carbon. And we see also that with increasing oxidation, we see an improved reduction of OMPs, and the oxidation potential needs to be adjusted to the biomass. We also optimized the treatment, pre-treatment of grassland, and this will be the last result. So we applied a mild base acid treatment to the grassland biomass with the aim that sodium hydroxide attacks silicon and aluminium, while acetic acid reacts with the other earth alkali metals and metals. And we achieved with the base acid treatment a reduction of 70%. So from 10% ash in the biomass, 3% in the generated press cake. And in comparison, the normal IFBB achieved only a 45% reduction. So we generated also activated carbon out of it, but unfortunately, we have only the UV A results so far. So we calculated the demand to remove 20% of the UV absorbance, and this is illustrated here. And in comparison, we used another high quality activated carbon, and I would only like to highlight the values here. So to achieve 20% reduction in the UV absorbance, we need 8.4 milligram of the commercial fossil-based activated carbon and 7.6 milligram from the grassland nature conservation area. So most likely we will also see a better OMP removal from the grass-based biomass in comparison to the fossil-based one. So with this, I would like to move to our summary and small outlook. In general, we are able to produce good activated carbon for wastewater treatment if we are using a feedstock with an ash content of less than 5%. If the ash content is less than 3%, the activated carbon will compete with the conventional fossil-based activated carbon. And this was not shown here. Grass-based activated carbon is highly mesoporic, which is beneficial for absorbing OMPs from wastewater. The next steps for us are definitely to develop specific biomass pretreatments to meet the above mentioned thresholds, also to gather better understanding of the adsorption processes on the activated carbon and interactions with the biogenic ones. And from the liquid phase, from the biomass processing, we are aiming to generate platform chemicals for plastic substitution. And of course, a big thing is to produce granular activated carbon to replace also their commercial activated carbons, and of course, standardization and upscaling of the whole processes. And with this, I would like to thank my team, uh, which you see here, which are not completed. I would also like to mention Nele. She's also in the audience for her work on the AC characterization from hedges and kitchen waste. And Lais, one of my PhD students, she started in beginning of this year. She will work on the platform chemicals, and of course the Ministry of Education and Research for funding our research group. And yeah, thank you very much for your attention, and now I'm happy to answer questions.
Thank you, Gabinian. That sounds all very promising. And my first question is, okay, why is no one doing that?
So basically, what we face at the moment is that we have a quite established technology or different technologies for biochar production on a small scale. We don't have reactor systems for activated carbon production at the moment. And also the companies who constructing pyrolysis plants are not really willing to further develop their system. We have one pilot plant which is located at the wastewater treatment plant in Baden-Baden, which could produce in general, which could be used to produce activated carbon, but it's not in operation now. And the big players in terms of commercial activated carbon, they are simply scared that they will not meet the quality standards. So we can clearly demonstrate there is a high fluctuation in the overall quality of activated carbons. And I really must admit, we are not able to sell an activated carbon with a surface area of 500 square meter. Nobody would buy it. So there are really some restriction from the global market. But there will be a shift, I'm pretty sure, because also the AC producers realize that they have to replace hard coal by biogenic resources, but they will focus on wood biomass. So we will definitely see a competition about wood resources, and I don't think that this is the solution. So.
And I was wondering, so you did a one-step pyrolysis and activation.
Yes. The main problem is since yeah, you can see it, so we have to compact in particular grassland biomass. So this is the generated press cake, and these fibers are not really suitable, so we have to compact them. And if we want to do a two-step activation, we have to compact the produced biochar afterwards again, because it decomposes. And I'm not sure if you can see this. It's not really pellets, and these are not pellets anymore. So there are a lot of fine powder. So two-step activation means we need a pyrolysis, then additional compactation and an activation again. And to be honest, the steam gasification works quite well. So
I was just wondering, you need a
yeah.
big steam activation reactor if you do a one step. Otherwise, you need a normal pyrolysis unit and a tiny activation unit.
Yeah, but then you need temperatures in the reactor above 800 degree, better 900 degree, and most of the producers are not using steel, which is or materials which are allowed to which are suitable to be operated under such high temperature conditions. So that's at least the problem we face at the moment. Yeah.
Have you tried going down to 800? I think 800 is the maximum that you usually want to use with your normal uh
Um,
yes.
we will do it. Yes, we will. It makes it a little bit difficult to control the temperature. If the reactor temperature is 800 degree, the gas temperature in the reactor will be a little bit lower. And we need these 900 degree in the gas phase or these 800 degree in the gas phase to allow the partial oxidation or the reaction of the oxygen in the steam and the carbon in the biomass. So to be on the safe side, I would operate a plant with a reactor temperature of 900 degree, assuming a temperature in the gas phase of a little bit more than 800. So we have a plant, we could use it. We will get it for free as a university. I only need a place for this plant and people who are willing to operate it.
But that's a good situation to be in, I have to say. Or better than not having the plant, but
Yes,
the other way
yes.
around is worse. There was one question in the chat. Did the feedstocks that went to the hydrothermal treatment had the same moisture content?
Um, Finally, I really must to say the moisture content from the initial biomass depends, of course, on the season, on the material, and so on. So we applied 4 times the amount of water in these hydrothermal conditioning, so 1:4 ratio biomass to liquid, for 15 minutes. So the biomass was completely soaked, all the biomass. And in the dewatering process, we achieve dry matter content of roughly 50% independent from the feedstock.
Okay.
So, but the initial feedstock, the orchard meadow, had a significantly higher dry matter content of roughly 50% already in the silage. So this has also an effect, of course, and it was definitely more matured than the wet meadow. Yeah.
Um, Now I forgot my.
And this has definitely an effect on the mass flows, definitely. So
Yeah.
and that's exactly what we are trying to standardize, that we know exactly from the biomass composition how we have to treat the biomass, and also to predict the outcome on terms of AC quality, so that we don't have to do all the experiments on a lab scale, so that we can simply predict it from the biomass.
And okay, one more question there. Do you add commercial chemicals to open up the pores of the AC? So any after production treatment, post-production?
No, we were not looking into chemical activation. So first of all, it requires a lot of chemicals. The second one is that we have to wash the activated carbon afterwards, and overall the process will be much more expensive, considering all the drawbacks. And also, we would like to go into green hydrogen generation, which which we could do by using steam as an activation. So we will have roughly 40% hydrogen in the syngas afterwards, which of course could be also used. But the main reason is we have an overall efficiency, or we are generating 10% of activated carbon per unit of biomass. So we have really a high mass loss. And if we go into chemicals, um, chemical treatment, we need a lot of chemicals. And in Germany, Switzerland, and Austria, we would you need around 40,000 tons of powdered activated carbon per year only to treat the wastewater. So which corresponds to 500,000 tons of biomass. So in my opinion, chemicals are not really suitable or not really sustainable in this dimension. Yeah.
Um, and just out of personal curiosity, any plans to look at the post-application alternative scenarios for burning spent activated, biogenic
Ye-
activated carbon?
Yes and no. So the state-of-the-art application of powdered activated carbon is to apply it in these in the adsorption stage for 30 minutes and to completely or to reach the complete adsorption capacity, it's recycled into the biological stage of the wastewater treatment plant and then removed by the excess sludge. And the sludge, the wastewater, the sewage sludge goes into the anaerobic digestion. And due to the recovery of phosphorus, it must be incinerated. So there might be an option to, it could be possible to separate the powdered activated carbon as well. So by not recirculating it. But then we have to dry it, we have to compact it again to do some activation, or of course we can dry it and use it in concrete to as a carbon sink. Of course, this would be possible. But I think from the economic perspective, it's not really feasible to do a reactivation, I guess. But
No,
we will we are definitely interested in running experiments with this approach as well.
yeah, well, I
Uh,
was more wondering, I mean, landfilling always sounds bad, but it's still better than incineration. And
it is, but if we consider that we gain energy out of it and it's bio-based energy, I'm not sure if then life cycle assessment would be better if we are using sequestration. We have to calculate it.
yeah, no, would be interesting because
Yeah,
also it won't do a lot in the AD reactor, I guess.
yeah.
So it's basically,
And also your hydrothermal reactivation could be an option probably. So you
yeah, I
published at
mean,
least one
it
project.
makes it maybe less dangerous, but I'm not sure if it's reactivated. Um,
Yeah.
but I mean, worth a try.
I must admit, I would be interested in doing, or we will do some research about desorption under anaerobic conditions. So this is not really investigated yet. And as soon as we are adding the powdered activated carbon into the digester, we have anaerobic conditions and no clue how the minerals will behave. So iron will be definitely reduced and no clue what will happen to the OMPs then.
Yeah, that's usually the baseline that the
Yeah,
OMP something is happening.
yeah.
Um, so thank you very much, Corbinian, very interesting. And if anyone wants to join the group, I think there's some opportunity there.
Yeah, we are still looking for an LCA PhD candidate, doing some LCA calculations, and a postdoc working on biochar and activated carbon characteristics in biomass. So if someone knows candidates, please let me know or let them know.
Come forward. So thank you very much, Corbinian.